All right, so today, let me just check I'm on the right document. Yeah. Okay, so today, I'm supposed to give a demonstration on something from the mini designs project. So don't forget you have something due in week 11, which is your assignment. And you'll produce like this report for the questions. You basically just have to solve like a trust problem. But yeah, you can look online on Moodle to see that assignment. It's called the mini design project. So I'm going to do a demonstration related to that. Because in the interest of time, I have like quite a few topics to cover. These three topics are all kind of big, especially these two. So I'm going to kind of just skim over this and then spend more time on these three. So these three are basically, I'm going to talk about how hinges work in frames and how they basically give you a bit more information in order to solve support reactions. And then I'm going to talk about for frames, how to solve for internal forces. So if you remember in week 3, we talked about beams and how they have internal forces like shear and bending.
Out of those three, which ones would be in your next?
I'll explain all of them and I'll tell you they'll all potentially be in there, but I'll tell you the breakdown of how the questions will look. All right, after I'll explain all of them first, and then geometric properties. Essentially, if you think about like a beam, right? We've just been assuming it's like a 1D member, like so. But we haven't really considered the 3D-ness of the actual beam. So in the context, so geometric properties is basically talking about the cross-section of the beam. So for example, if this is an I-shaped beam, we're calculating the properties of the actual cross-section in this topic. And it's kind of an introduction to solid mechanics, which you guys will be doing in second year. So it's an intro to solid mechanics. Okay, so basically, yeah. And what I was saying with frame internal forces is it builds off of the week 3 topic. Okay, so yeah, to answer your question, basically, how the next block test will look, based on the practice tests that you can see on Moodle now, is that there's going to be 3 questions, just like how there was for your first block test, right? And the first question is basically always a beam. So that's the week 3 topic. The second question is always a truss. So that's the week 4 topic we talked about last week. All right. And then for question 3, there's a 50% chance for a frame. And then, so that's what we're going to talk about today. And there's a 50% chance for geometric properties, which is basically also what we're going to talk about today. So I'm only going to cover stuff that's potentially going to be in your test, all right? So this stuff here, oversliding and turning and fluid statics, I think they're important, but they're not going to be tested, okay? Wei has mentioned that potentially in your third test, we will mention, sorry, not that one. We might mention friction a little bit, which is related to sliding, but that will probably be in the context of dynamics. So we'll come back to that, basically. So I'm only going to tell you stuff which is important, all right? So I'm not going to just teach you stuff which is completely irrelevant. All right, any questions about how your test might look or anything? All right, so let's quickly talk about the mini design project, okay? So in case you haven't had a good look at it, basically how the document looks is you have to select a structure, and for me, I'm going to be doing the demonstration case, okay? And for you guys, I believe there's 4 different cases underneath called like option 1 through 4. So you're only doing one of those, okay? Don't solve all 4 of those trusses, otherwise you're just wasting your time. So you're going to be solving 1 out of those 4, and I'm going to show you what it might look like in a demonstration case, which, to be honest, we're kind of holding your hand a bit too much because like basically doing the assignment for you. There's like extra bits which you have to do as well, So what I'm going to do is I'm going to show you the static load and I'll give you a hint on how to do it for the impact load as well, but you have to read the assignment brief really carefully. Okay, the reason why I'm not holding your hand that much is because it's kind of funny because in the previous year, we got in trouble for failing too many students in this course, right? And it's a first year course, so it's really brutal to fail because this course like builds, so other courses in the future like build on top of this course. So if you fail this course, like it's pretty difficult because this is a prereq for a lot of courses. And so I know you guys are only in your second term, probably most of you, but there's the idea of weighted average mark, right, which is your average grade. And let's just say, for the sake of argument, that is like 70 or whatever, over however long your degree goes for. Wei was saying that this course consistently scored 10 marks underneath people's weighted average mark, all right, but is expecting with the changes this year that it's going to be about 10 marks above your weighted average mark, okay? So he's purposely trying to make it easier. But if you think about the block tests and the breakdown of everything, so this is like block test 1, 2, and 3. Okay, the first block test was worth 20%. The second one, the one in week 7, is going to be bigger, so it'll be worth 30%. And the third one's worth 20%. And the assignment is also worth 20%, I believe. Is that how it works? No, something's wrong. I can't remember. I think the assignment might be worth 30%. Anyway, my point is, I'm doing this a demonstration case for you for this assignment, and it's already a large chunk of the assignment. Right, so like the code's getting way too easy. All right, so I'm not going to do the dynamic case for you like yet. You can ask questions once you start looking into it more. But anyway, for now we're just going to look at the static loads. So you have to read this table. So if you scroll past everything, there's like sections. So to do the first part of the assignment, you have to look at sections 1 and 3. For section 3, loading conditions, there's this table which says static loads, and for me, my last name is Z. Starts with Z. So I'm going to look at WL, which is just dead load. So weight of dead load is 12 kilonewtons. All right, and then you're told here exactly what you need to put in your assignment. So WDL is 12 kilonewtons, and so that's basically saying that 12 kilonewtons is applied every spot which it says on the diagram that it is. Okay, so this would all be like, this would be 12, this would be 12, this would be 12. And when you're looking at the dynamic case, you also have to consider the impact load. So it will be all those 12s and then also the impact load on top of that. And then the set geometry for this question, so everything's 4 meters apart. Okay, so before I like show you how to do the question, right? Based on what you know from what we were learning about last class, just have a look at this truss and try to figure out in your head what the zero force members are. Okay, so look at every node, and I'll give you like 5 seconds to do it. Just figure out the zero force members. Okay, so if you're looking at node F or node J, what you'll realize is there's two members connecting off of those nodes, and there's no external forces at that node. And so both of these end up being zero force members, like so. Okay, oh sorry, all four of those members. And the other one to look at is node H. So if you look at node H, there's 2 collinear members, and then there's a non-collinear member over here. And there's no external force being applied at that node. And so that non-collinear member is going to be a zero force member. So when you're doing your, when you've chosen your option for your truss, you're going to basically go through and figure out which ones are the zero force members first. That's the first thing you want to do basically, right? So that leaves the remaining truss like so. So here are all the truss members which we actually care about solving for that are non-zero force, okay? So the other thing to realize about this question is the symmetrical loading, right? Because due to the symmetry, we effectively only need to solve, and I'll just do this maybe in orange, okay? 1, 2, 3, 4, 5, and then 6. So we actually only have 6 members which we have to solve for, because as you can see, the ones that are highlighted in orange are going to be the same as the ones I'm doing in blue, right? It's just mirrored, okay? but you do have to state like how they're mirrored, which I'll show you in a second what I've done. But yeah, before you jump into like solving anything, you have to figure out, okay, am I doing method of joints or method of sections, right? Since we're solving for every member, we're interested in the axial force of every member, it'd be smart to do method of joints. And then you have to think about, for method of joints, where do I want to start my analysis, right? It's either from outside in or inside out, okay? So if you go from inside out, and let's say you start at either here or here, okay? So node H, you know this one's zero force, but you actually don't have enough information to figure out the members on the left or the right of that node. So you actually can't start at H. Similar logic goes for C, except there's just too many, I mean, yeah, it's just basically you can't figure it out yet because you don't have enough information. So realistically, you have to start at either support A or E. In which case, you have to work out what these support reactions are first, okay? So that would be the first step. You figure out the support reactions. You figure out that there's no horizontal external force, and so the horizontal reaction of the pin doesn't matter, okay? Or it's zero rather. And then, yeah, these two vertical reactions are taking half the load each. Okay, so there's 36 kilonewtons of load, right, going down. And so therefore 18 on each one have to respond and go up, okay, to balance out the system in equilibrium. So here, what I've done next is I've just written down the members which are symmetrical. So for example, let's say this one, member AB is equal to DE in terms of the internal forces, and so the same logic applies throughout the truss. And you've got the zero force members, which were just the ones that I've crossed out from earlier. We just have to explicitly state which members are zero force. All right, so these are just like formalities that you should do to make your working out clear. Okay, and the next thing is node by node analysis, right? So as I mentioned before, we have to solve for, let's say, the left half of the truss. And now we've worked out that this reaction, the horizontal one, is zero. And so you actually have enough information to go from A, okay? So you'll analyze node A, you do the vertical equilibrium, right? And you figure out force, you figure out force AG, and then you figure out AB using horizontal equilibrium, and you can choose to go to either node B or node G next. I would recommend going to node B, all right? Because remember there's a 12 kilonewton load. And so, yeah, you know AB already, and then you can figure out that AB is equal to BC, all right? And then you can figure out that, BG is equal to 12. You go up to node G, right? And then you can figure out, we know these ones, we know those two already, we just have to figure out these two, okay? And then you have every single member, all right? So I haven't done any of the maths, I just told you like the logic, because in the interest of time, I've got a lot to go through today. So I know I went like kind of quick, and that might make no sense if you didn't manage to catch the truss workshop from last week. If you have questions about it, I'll come around during the midway break, and we can break it down a bit further. But yeah, anyway, so you're just essentially trying to figure out the internal forces in the member. That's ultimately what you're trying to do, and figure out which ones are in tension or compression. And then that's the static case done. After that, you want to analyze the dynamic loads, right? And so that's basically, if you read the wording of the question, it says for the dynamic case, use the impact load together with the static loads, right? So you can't ignore the 12 kilonewton or whatever dead loads, and on top of that, you need to add the impact load, okay? And then you have to check whether your impact load is horizontal or vertical, and in either case, they'll tell you what the acceleration is. And we haven't really learned the particle dynamics specific formulas yet. So once we essentially learn kinematics and work energy methods, you can kind of solve this part, okay? But then it's just a matter of, trying to find an equivalent, a dynamic load which has an equivalent static force, right, and then applying it, and then resolving the truss. And then they literally, if you read this paragraph, they literally give you a hint on how to do the assignment step by step, but rather how to do the dynamic calculation. But I'm not going to do exactly how to do it. There's about 3 different ways you can do it. But like, yeah, can't have everyone getting 90 in the assignment, right? Okay. Any questions so far? All right, cool. So, first thing I want to tell you about is machines and hinged frames. Okay, so this essentially the idea is if we look at the supports on this frame, okay, you'll see that we've got a pin on both sides, right? And we've got, so therefore it's got a horizontal and vertical reaction. The thing is, because of the difference in elevation of these pins, you'll struggle to basically use the sum of the moments to find any of the supports, okay? And the other thing is we've got this kind of diagonal load on it. And so if we analyze the overall frame using kind of the methods that we've learned over the course, we're not going to be able to solve this normally, okay? There's too many unknowns basically, right? And we're trying to work out these reactions essentially, right? So we need to introduce a new method, and what we have to do is we have to realize that this frame is actually split up into 2 separate rigid bodies. The first one is this one-dimensional rigid body from A to C, and the other one is this 2-dimensional rigid body, which kind of bends like that. Okay, so from B to C. So these are connected by a pin or a hinge, okay? And what we essentially say is that we can split up the free body diagrams at this hinge connection and pretend that this hinge connection actually acts as a pin support, okay? For both the left and the right side, okay? The other thing, which I'll just show you once we've split it up, okay? So we've treated it like a pin support, right? In terms of its reactions, but what you'll notice is that where the hinge was, we actually have an additional bit of information, and that's that whatever the vertical reaction, for example, was at that hinge on the left-hand side has to be equal and opposite to the reaction on the rigid body on the right-hand side, okay? And so what you're gonna see is that because these are equal and opposite for both the vertical case as well as the horizontal case, is that we're gonna be able to use simultaneous equations, right, to solve for these forces at the hinge, all right? And then once we have the forces at the hinge, we actually solve for the support reactions, okay? So let me just run you through what I mean, because that was probably just like word salad. So, okay, what you might see is that if we look at these lines of action, all right, what you'll see is that, okay, maybe it feels like we might run into the same problem where no matter where we take the sum of the moments, we're gonna have more than one unknown left, okay? Do you know what I'm saying? So, for example, if I took the sum of the moments at A, I've deleted these 2 lines of action because of the lever arm being 0, but we still have 2 unknowns, right? However, if we do that on both sides, right? So if I take the sum of the moments at A and B on the for the first free body diagram and then for the second free body diagram, what you'll realize is we're going to be able to actually have this will end up as an equation which has 2 unknowns, and then there'll be an equation with 2 unknowns, but we have 2 of them. So we actually have 2 equations and 2 unknowns, and so we have a system which we can set up a simultaneous equation, right? And then therefore solve for all of those unknowns, okay? So let's do that. So I'm going to take the sum of the moments around A. One sec. So let's work out these lever arms. They're a little bit trickier on this first free body diagram. So if we look at the original question, basically what we're told is that we have the 600 Newton load in the middle of this kind of like rod thing. And this rod thing, the whole thing is 1.5 meters long. But since this force is applied in the middle, it'd be broken up into like 0.75 meters and 0.75 meters. The other thing we're told is that the rod is inclined from the horizontal axis at an angle of 60 degrees, right? So essentially, what you'll see is that we're going to need to find the lever arms of three forces, okay? The first one's this 600 Newton force, and the lever arm is going to be 0.75 meters. But then we're also going to find that we want the lever arms for, let's say, this force, right? Cx. And to find the lever arm or the perpendicular distance, we're going to need this side length of the hypotenuse triangle, okay? Sorry, the hypotenuse triangle, of the right angle triangle, okay? And so remember, in order to get the side length of it, what we do is we get the hypotenuse, right? So the hypotenuse of this right angle triangle is 1.5 meters. And we multiply that by sine to get the opposite side, 60 degrees, okay? So that gives us that side length. And let's say we want to work out the lever arm for CY, okay? And so therefore we want this side length of the triangle. We do the same thing, we multiply by the hypotenuse, and then we multiply by cosine, or the adjacent side. Yeah.
Instead of doing that, could you do the force is being directed at a different angle instead of finding another?
I kind of see what you mean. Do you mean like for example, C or something like that?
Yeah, like
You could, but the thing is, we actually. The question is, right? Okay. Like I kind of get what you're saying. Let's just go down that rabbit hole for a second, right? So the reason why it's a smart idea to break it up into the horizontal and vertical components is because if we go down the rabbit hole of setting this as like some arbitrary diagonal force, and then maybe on the other side you'd do like that, is you're actually not sure what the horizontal, like which components of the horizontal and the vertical component, like how big they are, and therefore you probably got the direction wrong. It's hard to explain. It's just smarter to break it up into the vertical and horizontal components, because the vertical and horizontal components are independent of each other, if that makes sense. It might make more sense when you see the next line of working out. But because I kind of get what you're saying, because I think in a few weeks ago we were talking about like, I can't remember exactly what it was. It might be like a roller support that was like at an angle. The thing is about a roller support that's at an angle is the horizontal and vertical components are not independent of each other, right? Because we know like a set perpendicular direction for that reaction. However, for this hinge, it behaves more like a pin. So if there was a pin, for example, at an incline, you would still set it as vertical and horizontal because the horizontal and vertical components are independent of each other. Does that make sense? Yep. So I would say don't do this. Okay. It's a good question though, because that's a pretty fair question to ask. Okay, so going back to this, we have to figure out which forces between these three go clockwise and counterclockwise. So remember, relative to A, let's look at the 600 Newton force first. So that one's going clockwise, right? So we're going to set it as negative. So we're going to negative 600, and then we multiply it by the lever arm, which is 0.75. Okay, next let's do, sorry, am I working out? I do CY. So let's do CY next, okay? So CY is also going clockwise. So we're going to go negative. And CY, the lever arm is 1.5 cosine 60 degrees. And then the next one, CX, is actually going counterclockwise, and so we're going to add it. Wait, what the hell did I do? Did I write the wrong one? Sorry. That one's supposed to be CY. This one's supposed to be CX, okay? So we're looking at CX, and CX's lever arm is going to be 1.5 sine 60 degrees, okay? So now, what you'll see is that we actually have two unknowns, as I mentioned before we might have, okay? So we have to rearrange this equation for just one of them, or at least this is the way that I do it. So we're going to rearrange it for Cx, okay? So Cx is equal to, if I rearrange this whole expression, it gives me this, okay? So it's going to be some kind of function of Cy. All right, so that is our first simultaneous equation, okay? So on the other side, the free body diagram on the right-hand side, we want to do the same thing. We want to take the sum of the moments around B because we want our expression in terms of the same things, Cx and Cy, okay? So there's three forces again. The other one that might be harder to see is the 500 Newton force over there. Okay, so here we go negative Cx, right? So it's going clockwise, and that's got a lever arm of 1. And we go negative Cy, because that's going clockwise. That's got a lever arm of 1. And then we add 500, because that's going counterclockwise, and that's also got a lever arm of 1. So what we're going to do is we're going to rearrange for the same variable. Okay, so we're going to move Cx onto the other side, like so. And then we're going to set that as our second equation, okay? So after we do that, we set these two things equal to each other, and what that means is the right-hand sides we're going to equal to each other, right? So that gives us this is equal, oh sorry, I covered it up. This is equal to this, okay? And so what we're going to do is we're going to set Cy, sorry, it's basically going to give us an expression in terms of only one unknown now, Cy. So once we group Cy together, we can actually rearrange it and find that Cy is equal to 97.4. Okay, so now, since we have one of these two variables, we can dive back into either our first or second equation and solve for Cx. It's a lot simpler to dive back into equation 2 if you just look at the two equations. So here I've recalled equation 2, and we literally just plugged in our value for Cy, which we found out, and therefore you can get a value for Cx, which is going to be 402.6 newtons, okay? So now, after doing all that, what we've actually done is, if I rub out all this scribbling, what we've actually done is we've removed these two unknowns, okay? So these are actually solved, so now these are known. And if you look at our remaining free body diagrams, okay, it means that we've only got one unknown going in the x direction and one unknown going in the y direction for both free body diagrams. And so therefore, you don't even need to take the moment equilibrium anymore. You can just take the force equilibrium, which is a lot simpler, and you can just solve for the remaining reactions, right? So it's basically saying all the horizontal forces are going to result in Bx, right? So that one. And then all the vertical forces are going to be counterbalanced by, By. And for the first free body diagram, same thing. We've worked this out, we've worked this out. So we look at all the equilibrium in the y direction and the equilibrium in the x direction, okay? Does that make sense? Yeah, I don't want to spend too much longer on this because our next topic is kind of like bigger. So get ready for the shit. All right, so I know I said there would be a break first, but I might do like a bit of this question and then take a break because otherwise, it might be really painful to go through this question in one go. Okay, so here's going to be a frame where we have to solve for the internal forces. And if you remember week 3, it was one of the harder topics you've seen so far, okay? So this is one step harder than that, all right? So we're going to be solving for, okay. What you'll see in this question is that we have to calculate support reactions, which we'll do. In fact, I've already done it because you guys are pretty familiar with that now already. But the other thing is that the question just tells us to draw the bending moment diagram, okay, and indicate the critical values. However, I'm going to show you in this question 2 other diagrams, right? So I'll show you the axial force diagram, the shear force diagram, as well as the bending moment diagram, which is what they actually ask for in the question, right? So what I'm going to show you is a longer version of what you might expect to see in your paper. It's just the reason I show you these is because they could potentially ask for the other ones as well as the bending moment diagram, okay? So I'm just trying to show you, I'm just trying to cover all the bases here, okay? So if we look at this beam, if we look at this frame, you're going to notice a few things. The first one is that there's a pin here, okay? And then there's a roller here, okay? So that's how we can work out all these reactions. Now the next thing is you have to try to figure out where there's discontinuities in your lines, okay? So when you have a uniformly distributed load, it's actually continuous, right? The beam is continuous for this entire region. So we've got one region from A to B, which is going to have some line which can describe its axial force, shear force, and bending moment. And then from B to C, we're actually going to have a new line, okay? And there's a discontinuity for, I guess, two reasons, but it results in the same discontinuity. One thing that can happen, which changes whether your line from back here was continuous or not. One thing that can change it is the fact that a uniformly distributed load stops. So if a uniformly distributed load stops, that's a sign that it's a new part of the beam, which has like a new line equations, okay? The other thing that indicates it is if there's a point load. So a point load also results in a discontinuity for your shear force, okay? And therefore your bending moment. All right, and then the other thing to note that's interesting is that the way that we're going to solve for this column essentially is we're going to solve it as if it was a beam, but we turned our head to the right. Okay, so what do I mean by that? So when we're doing these derivations of our line equations, just imagine a little dude, like an ant or some shit, walking along this beam. Okay, so it's walking, and then once he gets to point B, something different is going to happen. Okay, in other words, there's going to be a discontinuity here, and we're going to set up a new line expression, which is going to be cut BC, and we're going to reestablish where X starts. Okay, and I'll explain why later. But the dude's going to keep walking up until he reaches this edge, and then this is rigidly connected. So this frame doesn't have a hinge here. It's rigidly connected. And so what's going to happen is that you're literally just going to turn your head 90 degrees, and the dude's going to keep walking until he gets to over here, D, the support. So you're going to follow the beam like so. The frame like so, okay? So that's kind of the approach, and you'll see this in action, okay? You'll see how this works in action. So let's start with the easiest cut. So we're doing the left-hand side notation. In other words, we're going to consider everything starting from the left here, and we're going to make a new free body diagram for it, and that's this, okay? So what I'm saying here is that there is a cut, and it's moving from point A to point B, where X is in the domain of X is equal to 0 over here, and then where X is equal to 5. This is the line equation that I'm describing, okay? So yeah, over here on our left, we've got the support reactions, which we've worked out. We've got 10 kilonewtons acting towards the right. We've got 5.714 kilonewtons acting upwards, okay? So, and then we've got a distributed load as well of 2 kilonewtons per meter along the beam, pointed downwards, okay? So, what we have to do is, because I'm deriving the axial force diagram, the shear force diagram, and the bending moment diagram, I'm going to set all three internal forces to counterbalance, okay? So what I'm going to do is basically, if I, so our reference point's here, right? I'm going to solve it in the order of least complex to most complex, okay? So I'm going to start with the axial force. So to solve for the axial force, I'm going to take the sum of the moments sum of the forces rather, in the x direction. Okay, so we've got an arrow for axial force pointed to the right, so that's positive. That's the positive x direction, so it's going to be just positive n. And then I'm going to add 10 kilonewtons. So that's the 10 kilonewtons of the support that's pointed to the right. And if we just solve for this, right, you'll see n is equal to -10. That's going to be our first expression. So what that's saying is that just imagine you've got this beam and you've got this 10 kilonewton force that's pushing on it, right? Here is the response from the axial force, which is just saying that it's pushing back in and therefore it's in compression, okay? So that's how the system's in equilibrium. So we're in compression, okay? Compression with a magnitude of 10 kilonewtons, okay? All right, the next one is the shear force. So to solve for the shear force, we take the sum of the forces in the y direction, okay? And for shear force, with the left-hand side notation for beams, we have to set it as a -v. So we pretend it's an arrow pointed downwards, okay? So now we have to consider all the other vertical forces that we see. So at the support, we've got 5.714 kilonewtons pointed up. And then we've also got 2 kilonewtons per meter, except we have to multiply it by the amount of meters, right? In order to get this in kilonewtons. So remember, the size of this distributed load is going to change as we walk along the beam. All right, so from x is equal to 0 to x is equal to 5, it's going to get bigger and bigger. So the way that we derive this expression is we have to multiply 2, which is in kilonewtons per meter, by x. This is our variable distance, which is in meters, all right? And when those two things multiply together, it gives you the answers in kilonewtons, but it's like a variable amount of kilonewtons, right? Okay, so we're going to solve for v, which is just a matter of moving this onto the other side. And we find this gives us this expression. So this is the line equation for our internal shear force, right? Okay, so that's all good. Next, we're going to derive the for the internal bending moment, right? Which here I've called mx. All right, so it's going counterclockwise. So I'm going to set it as positive, all right? Another thing to note is that we're always going to take the sum of the moments about the cut, okay? So all of the force lever arms, which we're going to solve for, are going to be relative to their position from our cut, aka how far along the beam that we've taken the slice, okay? So what do I mean by that? Basically, let's take this force, for example, right, at the support, the vertical force of 5.714 kilonewtons, right? It's going to cause a clockwise spin about the cut over here, so it's going to be negative. Now, the next thing we have to do is we're going to multiply by the lever arm. Okay, so we know that's the magnitude of our force, right? We're looking at this arrow. We have to work out this distance, the lever arm, to the cut. Okay, and then that lever arm, we're going to realize, is going to be x, our variable distance. So the lever arm is going to increase as we walk along the beam. So that has to be x as the lever arm. Okay, the next one is the distributed load, right? So the distributed load is going to have an equivalent point load that's actually going to grow in size as we walk along the beam, right? Very similar to this concept from before, okay? So keep in mind, relative to the cut, this distributed load's equivalent force is pointing down, and it's going to generate a counterclockwise spin about the cut. And so therefore, we're going to add 2x. So why is it 2x? It's because the equivalent force is going to be the same. So that's the magnitude, as in the equivalent force can be the same as when we derived it for the shear. Except now we also have to multiply it by that lever arm. Okay, so in other words, the distance from our cut, which is moving, to the middle of that distributed load, which is also moving. Okay, so that lever arm is going to be x on 2, right? So half the distance basically that we've moved is going to be the lever arm. So that's going to be x on 2. Okay, so now we've accounted for everything. All we have to do is we have to solve for mx, okay? Just like before. And that gives us mx is equal to 5.714x minus x squared. So this is our line equation for mx, okay? All right, what I'm going to do, because I know I've been talking for a while, is I'll give you guys a break, and then I'll solve these other 2 parts, and then we'll talk about the question as a whole. So I'm going to come around and just make sure everyone's on the same page in terms of your understanding for this, because this is quite important for your test. All right, I'll come around. Oh, feel free to like go to the bathroom or whatever. Okay.
Do you think I can get that people?
Yeah. What's your name? What does that start with, sir?
D.
Okay. Oh yeah. Thank you. Sorry, what's your name?
Honest.
Is that with an R?
I.
Oh, I. Let me make my notes. One second.
Since then, whether it'll be here or not.
Oh.
Because I put like optometry building.
Uh,
So I suspect I might have to go pick it up.
might have to pick it up from where. Yeah, sorry, I don't have
Yeah.
it. That's all good. No problem. Sorry? Oh, yeah. Oh, sorry. I think this is like building on from week 3. I'm trying to go slow, but I know this is like one of the harder topics. Oh, sorry. So, you have the beam, right? So, show these reactions. So, and let's just say with a history. The idea is that the whole system is in equilibrium. Right. So let's just say this is like 2 kilonewtons per meter. This one is 3 meters. And let's say there's no horizontal forces, and so therefore there's no horizontal reaction, right? So this is 6 kilonewtons pointing down to and this is symmetrical, so this would be 3 kilonewtons pointing up, 3 kilonewtons pointing up, like that on each side. The idea with the concept of internal forces and equilibrium is if I took a slice of this beam and I just redrew it. Yes, exactly. So that still has to be 3 kilonewtons reaction. How is this beam like still in equilibrium in terms of it still has to be balanced in some way, right? So I'm going to call this distance x, how far along the slice. And the idea is that there's going to be a counterbalancing force called V, and V is called the internal shift V. And there's also going to be a counterbalancing moment, and then there'd also be a passive force, and
but in this particular scenario, that's going to represent your internal force. So, for example, if I push this pen together, that's compression. So compression is a type of internal axis tension. But we don't actually have any pushing in the axis of the beam, so that's going to be zero. So we don't need a for this particular. So this is the first scenario we kind of looked at. We just talked about the internal forces in the beam. The reason this is harder is because, well, it's actually somewhat similar to what we've looked at in Ruby 3 so far, but we're going to build on top of this since it's going to have more layers added on top of it. Yeah, so what we're doing is, because it's a variable distance, we're solving for the internal forces, but these internal forces are actually going to be a function of x. So that's what we're trying to do, trying to write as a function of x. And later we're going to graph them. Basically, similar to how you put x, y plane. Say we graph the shear force, and it might look, let's just say like this, for example. It'd be some kind of line equation of y is supposed to be, right? We're going to figure out what the y-intercept is, figure out what the slope is. Yeah. That's basically what we're doing. Except y, for our shear force and bending moment diagrams, is going to correspond to the German diagram. So let's say we're graphing shear force. The y-axis would be equal to b, which is the internal shear force. So I'll leave this with you. Further, yeah, that's good.
Yeah, I really thought I was asking. Yeah, question like things that are just figuring so I don't like instead of seeing the it's switched to that and then it ends up taking this one ends up taking 16. So it ends up like this.
Oh, yeah. It could be.
Yeah, that's what differentiating the
Can do it like that, and I've done it like that for some questions, but what I'll say is, because the question is basically just saying it's a hinge, you want to try to find the reactions. In my opinion, it's actually more confusing flipping around the free body diagrams too much. So I would keep the orientation the same to solve the support reactions. However, so are you support?
Yeah.
Okay. There's a course in second year called structural analysis, which is basically building on top of the first half of this house. So it means just in more depth. And there's some cases in that course where it tells you to find the axial force, the shear force, and the bending moment for similar questions. So as you can imagine, it might actually be simpler, like what you've done, to graph this part of the frame sideways, like diagonal, because your axial force is like the force is parallel to the beam. Your shear force is perpendicular to the beam. So it actually is smarter sometimes to reorientate these axes, right? But for the purposes of this course, I would recommend like shifting around the orientation of different body diagrams. Yeah.
Oh, do you want to show me up later to what you wrote?
Oh, yeah, for sure. I can show you now. Yeah, I can do it now. Oh.
I want just download the video. Go. Yeah. Yeah.
Sorry. So,
Yeah.
like, oh, okay, thanks. How are you?
Yeah, I'm good.
Yeah, how are you finding it? That's good. So on Saturday is a test. And then I'll do like some aspect. the other thing is that I went to get the exam first day. One was to come to our way, second one forward. Waiting time is right. Will just be some possible. How are you guys? You have any questions? You're holding it. So you want to give a paper? So your average mark, I think, over 3 tests has to be above 40. It doesn't have to be above 50. 40 to plus. Yeah. But it's the average, I think. As long as the average is above 40. But your total mark, including the assignment, has to be above. No problem. If you have any questions. Okay, just let me know. Okay, all right, what do you do? All right.
One second. Okay. Oh, I'm gonna put the microphone on. All right. So, let's continue with this question. So, what we're going to do now is we've looked at cut AB and we've actually derived the line equations for the axial force diagram, the shear force diagram, and the bending moment diagram for this part of the beam. And you'll see how that plays out once we're going to graph it all at the end. However, we need to now find line expressions for this part of the beam. So from point B to point C. So I'll tell you how we do that. What we do in essence is we consider everything from our starting point, so from way back at the support A, all the way till where we are now. You have to consider everything still, right? So everything, it has a memory of what happened beforehand, basically, right? And the other thing we do is we're going to reset where the starting point is for X, okay? And it's not obvious right now why we do that, but I'll just tell you. And then we'll come back to that, okay? So here's what I've redrawn. Our new domain is for X is equal to 0 to 2, all right? And we have now established that from A to B is like a set distance of 5 meters. And that new starting point for X was from B onwards, okay? All right, so we're going to do the same thing. We're going to derive the axial force first. Let me just get my phone. So we're going to derive the axial force first, and what you'll find is that N will be pointing to the right, so we're going to add it, and then we're also going to add 10. So just like before, the axial compression is going to be negative 10, which shouldn't be too surprising considering what we're saying is that from A to B, we're going to have 10 kilonewtons of compression, but from B to C, that 10 kilonewtons of compression is just going to continue, right? So it's going to carry on. Okay, the next thing to realize is we're taking the sum of the forces in the y direction to find the shear force, right? And so our internal shear force is pointed down. So we're going to do negative V. Then we're going to add 5.714, just like before. And then we're going to subtract 2 kilonewtons per meter, except now instead of multiplying by x, we're going to multiply it by 5. Okay, so it's a set distance now. Okay, so having done that, oh, sorry. Am I missing one? Oh, I'm missing the 10, sorry, yeah. There's also going to be 10 kilonewtons point load at B, which we have to account for as well now. Okay, once we do that, we're going to rearrange for V, which gives us negative 14.286. Okay, what does this tell us about the shear force? It tells us that the shear force from region B to C doesn't actually change. There's no change in shear force. And that shouldn't be surprising because from A to B, there was a distributed load, which has a continuous change of the shear force. But from B to C, there's no distributed load acting on it. So therefore, the shear force graph is going to be flat, all right, at that set value. All right, the next thing is we're going to take the sum of the moments at the cut to find the internal moment. So that's going to give us mx, and then we're going to subtract, let's start with this force over here, so 5.714. Except now, we have to figure out what the lever arm is from the cut to this force. And what you're going to find is that it's this distance here, right? This distance here is going to be 5 added on to x, okay? So now our lever arm is going to have a portion which is fixed, right? 5 meters. And it's going to have a portion which is variable, which we're going to call x, okay? And then we're going to add, let's do this force next, right? So the reason we add this is because it goes counterclockwise relative to our cut. So the magnitude is 10. And the distance, or the lever arm rather, is x. So here we're doing this force and this lever arm, which is just x, okay? Okay, and now there's one more to do, and that's going to be this distributed load. So this distributed load, interestingly, is going to have a set force now. Now that it's now that the whole thing is not going to change, all right? So we're actually going to do 2 multiplied by 5 again. We're going to add it because it goes counterclockwise. So this is the magnitude of our distributed load. However, what's going to change is actually going to be this lever arm. So the magnitude is not going to change, but the lever arm is going to change because we've got a component of the lever arm which is set. That's 2.5 meters, aka half of that 5 meters. But just like before, we're going to have a variable distance as well, which is going to be x. So it's going to be 2.5 plus x. So this whole expression is going to be our lever arm. Okay. Okay. So now, when we rearrange for mx, right, we find, and we simplify all of this, we're going to find this is equal to 3.57 minus 14.286x. What this tells us is the bending moment, the internal bending moment in this region is going to be linear, and the shear force is going to be flat, and the axial force is going to be flat, right, as well. Does that make sense so far? Yeah. Okay, so now we're going to analyze cut CD. So this is going to be a little different to what we've seen in week 3, okay? What we see now is that we've wrapped around the corner, right? And if we imagine our little dude, or you can imagine an ant or whatever, we have to orientate all of our internal forces 90 degrees because we turn the corner 90 degrees like so. And so as a result of this, a few things happen. The first one is that x is now, it starts from this kind of datum and then points downwards. So as we increase x, it walks down the beam, or you can think of it like a vertical beam, or you can think of it like a column or something. And what you'll see is that all of the internal forces shifted too. Okay, so what do I mean by that? If we look at the left-hand side notation, normally it looks like this. So we've got our internal shear, our internal axial force, as well as our internal moment. Once we rotate this 90 degrees clockwise, this results in this orientation of these internal forces, okay? So what you'll see is that the shear force, right, is now pointing left. The axial force is now pointing down. But our internal moment is actually going to stay the same in terms of its orientation, because the internal moment is going to remain as counterclockwise, right? So I'll show you what this looks like in the bending moment diagram later, but the idea is that the internal moment actually, we consider this as continuous around the corner. We consider the bending moment continuous around the corner. Okay, so let's start with the axial force. So for axial force before, we were thinking of it like the horizontal forces resulting in axial force. But if we're analyzing a vertical member, the axial forces are actually going to be vertical, right? So instead of taking the sum of the forces in the x direction, we take the sum of the force in the y direction, and that's going to help us solve for the internal axial force now. So how this is going to change things is before, all right? Well, before we had sum of the forces in the horizontal direction is equal to positive n, right? Now it's negative n because remember, our arrow is now pointing downwards, right? That's one thing. The second thing is that we, instead of considering the horizontal forces like we had before for axial force, like the 10, we're actually looking at all of these vertical ones now. Okay? So all of these vertical ones is going to result in a much different axial force. And as a matter of fact, this is kind of essentially the main difference between beams and columns. So beam, right, being a horizontal member, looks at the horizontal forces for its when considering its axial forces. But a column, to consider its compression, or the compression in the column, you have to analyze gravity loads that enter the column. All right? Does that kind of make sense? Yeah. So, yeah. The orientation of the member dictates kind of which forces it's absorbing, is what I'm trying to say. So here, what I've done is I've collected all of those vertical forces, right? And so what we're going to find is that the axial force is equal to 14.286. So this is still in compression, but it's a different number because it's absorbing different external forces. All right, next we're going to solve for the shear force. And what you're going to see is that the shear force, we're actually pointing to the left. Okay, so we're going to do negative V, right? Because we're taking the horizontal sum, pointed to the right as a positive direction. And then we're going to add on 10. So we're going to add on 10, and that's due to the horizontal support reaction. And what we're going to do is, because now we've actually got a distributed load that's pointed to the left as we go down this column, right? We've got a magnitude of 2 and it's pointed to the left, so I'm going to do negative, and it's got a variable distance of x, okay? So now, if we solve for v, the shear force is equal to 10 subtract 2x, okay? So now that's our line expression for our shear force, okay? Okay, the next thing is summing the moments about the cut. And what this looks like essentially is, it's actually quite similar, because what I'm trying to say is if we were taking the internal forces when we were looking at like these beams basically, versus if we're looking at this column, not much changes because we're still taking the sum of the moments and we're still considering the counterclockwise direction as positive. So we're going to do mx, and then we're going to subtract. Now we're going to do 5.714, except now we have a fixed distance, right, for this lever arm. So before this was a variable distance, and now it's a fixed distance to this vertical support reaction, right? It's 5 meters plus 2 meters. Okay, and then let's consider this force next, right? So this force generates counterclockwise spin, So we're going to add it, and then we're going to multiply it by 2, because just like the 5 plus 2 meters for that lever arm, now we just have a fixed lever arm of 2 meters as well. And then let's consider the equivalent point load for that distributed load. And just like before, we have a fixed magnitude of 2 meters multiplied by 5 meters. Okay, so that's the magnitude. Sorry, I'm covering that plus sign. That's the magnitude of that distributed load. And now we also have a fixed distance. Okay, so the distance is going to be 2.5 plus 2. All right. Okay. The next one is going to be this horizontal force. Okay. So this horizontal force is going to cause a clockwise spin about our cut, and so therefore it's going to be negative. All right. However, here's where we have to consider the variable distance x. Okay. So this 10 kilonewton force is going to have a shifting lever arm, right, relative to our cut as we move down this column. And the next one to consider is this distributed load. So this distributed load points left, and it's going to grow in size as we move down the column, and it's also going to increase in lever arm. So what that manifests to is, firstly, it's going to be positive because it goes counterclockwise, and its magnitude is going to be 2x. So 2x is the magnitude of this arrow, basically, and the lever arm is going to be x on 2. Okay, so just like that. All right. So now we have this big ass kind of like equation for the internal moment, and if we solve for mx, we get negative 25. I have some rounding error here. You can include it, or you can just write 25, up to you. And then all these other terms. Okay, so that is our internal bending moment equation for cut CD. Okay, so that's basically a really long line of working because it's including and considering every single force that we've seen along the beam thus far. Okay, so how do we actually graph these things, all right? And the best way for me to explain this is just by showing you visually and just highlighting things, okay? So the first thing I want to show you is the axial force, right? So here's a free body diagram in its entirety. I want to show you how the axial forces are graphed, okay? So from cut AB, like from A to B along the beam, we've got negative 10 for our axial force, and for B to C, all right, we also have negative 10, all right? From C to D, which is the vertical part, here to here, we have 14.286, all right? And so all of these are flat numbers, and so for our axial force diagram, it's going to look like this, all right? The idea is that from A to B is going to be negative 10, from B to C is going to be negative 10, and then from C to D is going to be negative 14.286, right? The next one to keep in mind is the shear. It's the internal shear. So from A to B, we've got a shear which follows a linear curve. It's like a straight line. And it's going to have a negative slope, right? This slope of negative 2 is equal to the distributed load. So what does that look like? That looks like this line. So what I want you to do is I want you to link this to what you've kind of learned from like year 10 maths, basically, right? We've got the y-axis being represented by v, and we've got the x-axis represented by x. And if I wanted to find a line equation, right, y equals mx plus b, b is the y-intercept, and so b is 5.714, right? The slope, m, is negative 2, right? So that's negative 2, and that's the same thing as your distributed load magnitude, right? Okay, so that's shear force from A to B. Shear force from B to C is a flat number of of negative 14.286, and it's going to be represented by this flat line. Okay, now there's a jump from this number to this number due to the 10 kilonewton point load that goes down like so, right? And then around the corner, the shear force is going to change because it's going to shift in terms of the horizontal / vertical force, right? So our last line equation is going to be represented by V is equal to 10 minus 2x. And what that means is basically now we're considering shear positive this way and x is this way. Okay, so it's going to start at positive 10 and it's going to have a slope of negative 2 going down until it reaches the horizontal, well, not horizontal, the x-axis basically, right? Okay, now the hardest one to understand is probably the moment diagram. So the internal moment is equal to this equation from A to B. So this is a parabola, like so. And if I wanted to find the maximum moment at the peak of this parabola, what I would probably do is essentially refer to the shear force, because remember where the shear force is 0 means there's going to be a flat part in your parabola for your bending moment, right? And so I want to find the value for x, which gives me the peak of this parabola. Okay, so what I can do is I can look at this equation here for v, and I want v is equal to 0, right? So where where the line touches the x-axis, right? So if I set 0 is equal to 5.714 minus 2x, and I solve for x, all right? I've actually done it down here. I get x is equal to 2.857. So what that's telling me is that if I travel 2.857 meters along the beam from A to B, I get the point where shear force is 0, and therefore it's also where your bending moment is at its peak. Okay, so if I plug that number into my moment equation, in other words, if I look at this expression, and every time I see x, I plug in 2.857 meters, and then I get the output, I can find the max bending moment in that region, and it's 8.162. All right, so that's if I wanted to find the peak of this bending moment curve. All right, so next, if we analyze the part of the beam of the frame from point B to C, and we're looking at the internal bending moment, we have this expression. So what we see is that now the bending moment is a straight line, okay, with a y-intercept of 3.57 and a downward slope of 14.286. So we can just graph that like a straight line equation, like so. All right, and lastly, the bending moment around the corner has this final expression, and you can see it's a parabola, and the parabola starts at negative 25 and works its way up to 0, right, once we plug in x is equal to 5. Okay, so yeah, there's a bit of rounding error. You can do negative 25 here if you prefer, up to you. But yeah, does that make sense? So that's how everything ties together in terms of solving for all the internal forces for frames, right? So that's how you would do it for a connected beam and column system. It's super time consuming to do it for bending moment, axial force, and shear, but I'm just showing you because this would be essentially the hardest thing they can ask you in your week 7 test, okay? So I'm showing you the hardest thing. Once you do your practice, you'll find that it's easier than this because there will be less things to solve for, all right? Some extra bits of commentary I want to add on top of this is, yeah, so as I mentioned before, this is complete overkill. Just figure out what they're asking for. So in this particular question, they were only asking for the bending moment diagram. Just solve for the internal moment. In other words, I wouldn't even bother drawing the arrows for shear and internal axial force. Yep.
You know, an equation of the previous page.
This one?
Yeah, if you solve that, wouldn't you get two solutions?
Oh, yeah, that's a really good question. Okay, so you're right. Okay, I'm going to make this simpler by graphing this on an xy plane and just orientating it like this, okay? So here's the x dimension, here's mx, right? mx, I actually don't like this notation. It's technically m as a function of x, but anyway. Okay, so you're right. What happens is, it's parabola, okay? But what you'll find is that it's a parabola which only has one root because it's a perfect square. So at x equals 5, that's the only point which it touches, I guess.
But what if like a question isn't a perfect square? What if that has two roots?
Yes, good question. So essentially what happens is, let's say there's a parabola that looks like that, okay? So let's say, just for the sake of argument, that at x equals 7, and then over here, x equals -2, here's the roots of the parabola, okay? The thing is, it doesn't really matter because we're only graphing the positive parts, I guess. So let's say this is point A on a real beam, and let's say this is point B. We'll only be graphing this region anyway. So if there's a negative root, we just kind of ignore it, if that makes sense. Yeah. So we're only, even though this is like in a, like a mathematical space where you consider the negatives for an x-axis, you can think of it as parts of the parabola which are excluded. But for the purpose of graphing bending moment, we only look at the real and positive numbers.
Okay, this might be a bit of a stretch, but what if like both of the roots are positive?
Oh, that's still graphable as well, because let's say it's like that. Sometimes your bending moment will be negative here and then positive here. You would still capture everything. It doesn't really matter where the roots are. You're just trying to capture the bending moment from x is equal to, let's say, 0 to whatever you're interested in. Say point A and B are 7 meters apart. All right, you just graph everything from your domain of interest, which might be x is equal to 0 to x is equal to 7, for example. Yeah. Good questions. It's very, very good questions indeed. All right, so going back to this, one more thing I want to say is, look, for clarity in the answers, they flipped it, all right? And yeah, this is basically the short answer. You'll learn in second and third year and stuff other reasons why they might flip the bending moment diagram, but just for the purposes of your course now, you're allowed to flip these bending moment diagrams so that the graph is potentially clearer. Okay, so do you see how, like, around this corner, it doesn't overlap as badly? Okay, you're allowed to just flip it for the sake of clarity if you would like. Okay. The other thing to note is the bending moment diagram is continuous around bends if you don't have any point moments and if you don't have a hinge. Okay, so like this is rigidly connected, right? So you've got the beam and you've got the column. Whatever number it is around the bend will continue. Okay, so that's just because our internal bending moment orientation doesn't change, right? Whether we're 1 millimeter to the left of point C or 1 millimeter down from point C, the orientation of the bending moment, internal bending moment, doesn't change. Okay. Okay, so that's the hardest topic out of the way. Here's the second hardest topic. Alright, so I know I've only got 30 minutes, so I'll try to make good use of time. Let me give you some context first, alright? So we're going to do geometric properties, and what I want you to think about is imagine you're crossing a river or something like that. Okay, and so there's like water and crap there. Let's say you've got a piece of wood that can be orientated like this or like this, okay? So one way is, I guess, well, this way you've orientated the wood flat, and this one it's on its edge, okay? So if I was to walk across this river, right, which bit of wood would sag more? Which bit of wood would be less stiff? Yeah. Yeah, the one that's orientated flat, we can intuitively tell is going to sag more, right? So what we can say, we want to establish this concept of a bending axis, okay? Bending axis. So this bit of wood is bending perpendicular to this line, okay? And that's important. So bending axis is perpendicular to the direction of the force which would cause it to bend, okay? So that's one thing. The other thing is this concept of stiffness. Let's call it bending stiffness, okay? So bending stiffness comes from two components, all right? E multiplied by I. E, as you may or may not have heard of before, is your elastic modulus, and this is a material parameter. Okay, so for example, if this beam was made out of steel, you can imagine it's stiffer than if it was made out of wood, right? It's got a higher elastic modulus. However, the other thing that controls it is this idea of area moment of inertia. And this is actually a shape property. In other words, in the formal word that we use is geometric. And that's what we're concerned about today. Okay, so we're going to work out the shape stiffness, right, of various shapes of beams, all right, or whatever that you're bending. Okay, so we're concerned about the area moment of inertia. Now, it's conventional to essentially, so if we're considering two different axes like so, it's conventional to call the stiffer axis the XX axis, all right, and the less stiff axis the YY axis for bending, okay? We're kind of taking baby steps into solid mechanics. So solid mechanics, as I mentioned before, is a second-year course. I think it's called ENGG1300. All right, we're just doing like not even half of the first week's topic in it, right? So this is geometric properties. Okay, so now that I've given you some context, I basically need to tell you about three things related to it, right? The first one's the centroid. The centroid is the center of area, okay? So imagine I've got some random shape, and here's my finger. What the fuck? And I'm trying to balance this shape on my hand, okay? I'm trying to find its center of gravity, right? The center of gravity of this, let's say this is like a piece of cardboard or something. The center of gravity is the center of the shape in this scenario, okay? So that's what I want you to think about. And this is the idea of a centroid. The centroid is simply explained as the center of area, okay? So this is the first concept I want you to think about. For example, if I wanted to find the center of these two rectangles when you consider them together, the center might be out here somewhere, okay? So remember, this shape does not exist in isolation. The idea is that we're calculating the cross-sectional properties of a beam, okay? So for example, this might be an L-shaped beam. And what this might look like is, if I was to draw, the beam like so, what we're actually drawing, I'll color code it. Fuck. We're actually drawing this L-shaped beam like so, right? And we might be looking at it from over here or something like that. And we're essentially concerned about this cross-section, this here, right? Does that make sense? So that determines its bending stiffness and other properties. So we want the center of area, and there's two ways to get there. The first one is trying to find it as a continuous function or like using calculus and integration. I wouldn't recommend doing this for the shapes which you're going to be presented with in this course. So in this course, we only deal with rectangles, okay? And if we're dealing with simple shapes like rectangles, you can add them together in a discrete manner, okay? If you had like some weird function for a shape, you would deal with it using integration. But I would just simplify it and do it in the discrete way. Okay, the second thing to do to understand is this concept of moment area of inertia. Oh, sorry, other way around. Area moment of inertia, which I briefly explained a second ago. This is the exact same thing as the concept of second moment of area. So these two phrases are interchangeable. All right, second moment of area is the same thing as area moment of inertia. One simple way you can think about the formula and how it was derived is you take the area and it's the multiplied by the lever arm squared. So second moment of area being, because you know how for forces you have moment times your lever arm or whatever. It's second moment being multiplied by the lever arm twice. Okay. So that's basically where these expressions come from in a kind of generic expression. And as I briefly mentioned before, you would have major or minor axis bending, right? Being, for example, for a steel beam, which might have this I shape, if you were to apply a force perpendicular, let's say you applied a force like so, it's bending around this axis, the XX axis, right? It's different direction. Whereas minor axis bending would be caused due to, let's say, a force applied to the right. It's going to cause it to bend perpendicular to that axis, right? So like physically you would see this beam bow out like that. And then for this one you would see it kind of curve down like that, right? If I was to look along this. Yeah, anyway, you kind of get it. Okay, so for this course, we're only going to deal with discrete rectangle shapes, okay? So for your moment of inertia, this is simply going to be BD cubed on 12 if it's bending about the x-axis, like so. If it's bending around the y-axis, oh shit. That's my supervisor. So, if this is bending about the y-axis instead, it's got a slightly different formula, right? So it's b cubed d on 12. Okay, so I'm not going to derive why this is over 12 for a rectangle, but you'll see later I've shown you why, like the constants for different shapes. Just expect to see the rectangles in this course, right? Okay, so that's simple enough. Now I need to explain parallel axis theorem to you guys, and this is probably the hardest concept to kind of understand, and it's easier to see. Okay, actually, no, I'll give you an example first, all right? So just imagine the scenario with the river, okay? And let's say we're gonna do this major axis bending orientation, all right? Except instead of a rectangular section, we're gonna do an I-beam, okay? So you've got this shape, and it's bending around this axis, right? And it's got a certain stiffness, right? And you've also got another option, which is like so. Let's just say this is like some kind of made-up shape. Which one has a higher stiffness when bending around the XX axis, do you think? The shape on the left or the shape on the right? This isn't like terribly intuitive, but I just want you to think about it. Which one is going to bend less? Yeah, when crossing the river. It's actually the shape on the left is going to be stiffer. So it's not exactly intuitive as to why right now, but the answer lies in parallel axis theorem. The idea is that you have these three rectangles, right, which contribute some amount of stiffness. However, what we have to do whenever one of these rectangles doesn't lie directly on this line is we have to apply a formula which adds additional stiffness based on how far it's shifted, okay, perpendicular to this axis. So this is the concept of parallel axis theorem shifting. And so what I'm trying to say is that because this rectangle, for example, has only shifted a little bit away from the bending axis, right, it's going to contribute less stiffness than this shape. So what I'm trying to say is the reason why you see a lot of steel beams, you know, in real life, is because this is one of the reasons why it's a heavily optimized shape, right? You're putting as much of the meat, I guess, of the cross section as far away from the bending axis as possible, and therefore you're going to give it a higher stiffness. Okay, so you'll see why due to the formulas, but it's easy to see once we do the questions. Okay, so I'm a bit conscious of the time, so I'll try to go relatively quickly. Okay, so the first question here, we're trying to find the centroid, which what we can see here is that our coordinate system starts in the very bottom left, and we've got two shapes. All right, we're trying to find the centroid, and we know that it's roughly around here. Okay, so the center of these two shapes that form this this L-shaped beam, right? Okay, so what we have to do is we have to find a way to divide the shape so that we don't double count anything. So we can split it into two rectangles. Here's one way to split it, which is the way that I've drawn it. The other way to split it, which is perfectly valid, is chopping it this way. Okay, so as long as you don't double count the way that you've split up your shape, you'll get the same answer. Okay, so for shape 1, it's going to be, so the overall formula which we're concerned about when finding the x-centroid is the sum of the area multiplied by its x-coordinate over the sum of the area, and we have to sum this for all of the elements, okay? We've only got two elements, right? So we'll do the area of the first element, right? And it's 5 millimeters, so all of these are millimeters. It's 5 millimeters wide multiplied by 100 millimeters deep, okay? And now we have to multiply it by the x-coordinate. And so what do I mean by that? How far along is the center of this shape relative to the start of our coordinate system? And the answer is 2.5 millimeters, okay? And then since we're summing everything, we're going to add the next thing on. And we essentially have to do the same thing. So we have to find the width, and you can see that the width is equal to 100 minus the 5 from the thickness of the first rectangle. So that's going to be 95. Okay, so 95 thick multiplied by a depth of 5 millimeters. Okay, and now we have to find the center of this rectangle, right? And so there's basically two components to it. We've got a dimension of 5 mil due to the first shape, and then we go halfway across our second shape, so that's going to be 95 divided by 2, right? So we'll go, we can go like 5 plus 95 over 2. So that's going to give us our x-coordinate, the center of the second shape relative to our 0, 0 coordinate. Okay, and then for the bottom of our fraction, we're going to add the areas together. And we've actually calculated the areas, so what you'll see me do is literally just copy the exact same working from the top, except exclude these parts, which is the x-coordinate, okay? When we compute this on our calculator, we get 26.86 mil, like so. And basically, if we do the same thing in the y direction, you can follow the same line of logic, except there's actually a line of symmetry here that allows us to take the exact same centroid value, all right, for the x and the y direction. Does that make sense? Okay, so essentially we've actually found the centroid now. It's basically saying from this point we go 26.86 to the right and we go 26.86 up, and that will give us the center of our shape. Okay, so let's move on to the second example, and this is basically how we find ix and iy. Okay, so here we've got 4 shapes, okay? We've got 4 rectangles. So what I'm going to do is I'm going to group these together. This might take a second, Sarah. Because I want you to be able to think about this visually, all right? This is the best way to learn it, in my opinion. Because if people are just following a formula, it doesn't really make too much sense. What I'm trying to say is that for these 4 shapes, if we duplicate them and move them over here. Okay, we're looking at the XX bending case first, right? So there's going to be, let me do it as a dashed, like a straight line like this. So we're looking at XX bending first, okay? What happens when we put in our formula, which involves doing, like, for example, BD cubed on 12, right? We do BD cubed on 12 for all 4 of these shapes. And what happens is they actually, like, quote unquote, spawn in on this line, okay? They'll be like spawned in and they'll all kind of be overlapped, kind of like so. And what we have to do is we have to shift them into the correct spot, all right? So this is parallel axis theorem shifting. 4 was down here, so, oops. So 4 has to be shifted down to like there, okay? 2 has to be here, I think. 3 has to be here, and then 1 has to be up here, or whatever, okay? Now, here's the thing. We only care about, for calculating Ix, so the moment of inertia in the x bending direction, we only care about the perpendicular distance that we've moved our shapes, okay? So we only care about the lever arm for shape 1 and shape 4. 2 and 3 doesn't actually matter for Ix calculations. The idea is that you're allowed to move along this parallel line for free. Like, it doesn't contribute any additional stiffness for major axis bending. Okay, so we're concerned about adding this lever arm. Okay, so how this manifests in the working out, what I'm trying to say is that, and in my working out, there's 2 lots of a bunch of things, right? You'll see there's 2 kind of like horizontally orientated rectangles and 2 vertically orientated rectangles and 2 lots of parallel axis theorem shifting, which are equivalent. Okay, so what I'm trying to say is that we have to basically spawn in these 2 horizontal shapes. So this one will be the purple one. So we'll go BD cubed on 12. So B being 50, right? D being 5, okay? We cube it and we put it over 12, okay? For the second one, we go B, which is 5, so it's 5 wide. It's 90 deep, and it has to be cubed and then over 12. So this is 2 lots of the blue one. And now the last one is 2 lots of parallel axis theorem shifting. So the formula for parallel axis theorem shifting is you take the area and you multiply it by the shifting distance and then you square it, okay? So here's what we're going to do. We're going to do 2 lots of the area, right, for shape 1 and 4, which is 50 multiplied by 5, okay? So that's the area. And we multiply it by the shifting distance, all right? So let's think about the shifting distance for a second. We're moving it from here to here, all right? And that's going to be 50 subtract half the thickness of that element. So it's going to be subtract by 2.5, which results in 47.5. Okay, so that's our shift distance, and then we have to square that shifting distance. Does that make sense? So the higher this number is for a moment of inertia, the more stiff our beam is going to be, okay? All right, so that gives us 1.737, okay? And yeah, now I'm going to show you what it is for the YY bending case, okay? So essentially, here's how you have to think about it, okay? So instead of calculating the bending around the XX axis, now we're calculating the bending around the YY axis. So we have to basically rethink about our orientation. All right. Now we're bending this way. Go YY. So when we spawn in our shapes, we're following this formula instead. We go B cubed D on 12. All right. So it's slightly different. And once everything's spawned in, it's going to be like here and whatever, okay? what's actually going to happen is we can move shape 1 and 4 up and down for free. Okay, so there's no shifting distance. What happens now is that shape 2 has to be shifted to the left and shape 3 has to be shifted to the right. Okay, so essentially we're concerned now about the shift distance for shape 2 and 3. So let's call that shift for shape 2 and shift for shape 3. Okay, so this is the way we have to think about it now. All right, so just like before, we've got 2 lots of the horizontally orientated rectangle. So that's that. We've got 2 lots of the vertically orientated rectangle, which is that. And then we've got 2 lots of shifting, except now for shape 2 and 3. So now this is shape 2 and 3's area, and this is shape 2 and 3's shifting distance, right? So it's going to be 22.5 now. It comes from the fact that this whole thing is 50 wide, and then we're shifting to here. So we go 25 minus 2.5 because the thickness of that rectangle was 5. Okay, so that gives us 22.5. And when we compute that whole thing, this is the number that we get, okay? All right, that brings me to the end of the workshop. I'll show you what the next few things are, right? That I didn't get to. Give me 1 second. Oh, fuck, wrong document. Sorry. Okay, here's a few things which I didn't get to talk about this lesson. The first one is that was one approach that we could take for this, and I was just demonstrating that to show you how parallel axis theorem works. If I wanted to get this hollow rectangular section's cross-sectional properties, another way that I could do is I could take the outer rectangles BD cubed on 12 and I can subtract it by the void space. Okay, so this is the whole idea of superposition, which I might have mentioned in week 3. The principle of superposition also applies for geometric properties. So I can subtract the void space's stiffness and get the answer that way too. The other thing is at the end of this document, what you might find useful is from when this course used to be broken up into 2 midterms and a finals. Now it's broken up into basically 3 midterms. But you might find the static quizzes as good practice as well. So here I've got a beam question that you could follow through. Here I've got a truss question that you can follow through. And I believe this is just another beam. All right, cool. So that brings me to the end of this workshop. So yeah, I'll stop recording and feel free to ask questions and stuff.